lastly, I would like to introduce Simon up again, but with a different hat on. So I think someone mentioned Steve before, so we thought we would throw him up as well. I won't say where this image came from or when it is, because I actually don't know.
A couple of years ago.
It wasn't from my...
Steve, you should come up here and see who's aged best.
We'll do a competition later. All right, up to you, Simon.
Okay, thank you very much. Thanks to Luke for that talk and for Sibby for the one before. I'm going to go in a totally different direction from where these guys are coming from. What I'm going to talk about now is eyes. We talk about photonics, we talk about light. Eyes are the basis of our sensing of light. And so I'm going to talk about a company that we started a few years ago called Sci-Light. If you're good, you can sort of work out Sci-Light up here somewhere, hidden in there. And we make this machine here, which is a machine for measuring eyes. And what that can do is to generate this sort of this sort of thing here, which is a 3D volume image of an eye. Now you can see the cornea at the top, the iris there, the lens, and down at the back here, that bit is the back of the lens where there's cataract, which is basically a blurring, a crystallizing of the lens. And we'll talk a little bit about how the sort of things we can do with this machine are going to change the way that we think about measuring eyes. The eye health is an amazing problem. It's a huge problem. A third of the population of the planet live with some sort of vision impairment, whether it's a short-sightedness, long-sightedness, cataracts, the impairment of the retina, degradation in other areas. And 75% of that is avoidable or treatable if we can get the technology to be able to measure, to quantify, and to address some of those issues. Also, really important, half of the world's blindness is caused by cataracts. Here's a picture of somebody with a cataract. It takes 20 minutes to do an operation to pop a new lens into somebody's eye. It's kind of gory when you see somebody slicing an eye open for the first time and popping the lens out and putting a new one in whilst you're eating your breakfast. But you get used to it. But it's a really important point. This is a massive problem. That's talking about cataracts. It's typically a disease of older people. So people like me, I've got incipient cataracts in both eyes. I didn't know that until I actually peered into our machine and it told me. I don't really want to know that, but it's not a problem yet. And being first world, I can pay somebody to fix that for me. There's something like 3 million cataract operations a year in the US. 3 million implantations of new lenses into people in the US. It's a huge market opportunity if I put my business hat on. The other really scary thing about eyes is myopia. Myopia is the unknown problem that nobody likes to talk about. Optometrists and ophthalmologists know it because it is a huge problem. It is a huge and rapidly growing problem. It's short-sightedness. People are becoming more short-sighted. In East Asia, where this is the worst, there's a genetic component to this. In East Asia, 60 years ago, 10–20% of people, by the time they reached 20 years of age, were myopic, my short sight, had to wear glasses. Now it's nearly 90%. Over 90% of the people going into the Korean army for their national service are now short-sighted, up from 10 to 20% just 50 years ago. And same in the US and Europe. It's not just an Asian problem, it's a global problem. It's doubled over the last 50 years in the US and Europe. Why? There's a lot of reasons why, but it basically comes because we're not living like we used to. We're spending more time indoors. We're spending more time looking at things about this far from our face. We're not focusing on infinity. We're not getting sunlight. We're not getting the vitamin D generated. We're not getting the eyes to develop in the way they used to because we're spending time indoors looking at things that way. It's driven, particularly in Asia, by growing affluence as well. People want their kids to do well, so they make them work harder, spend more hours reading books, staring at computers. Lots of societal as well as sort of genetic reasons for this. So it's a real problem. We need to worry about myopia. That needs to be, you can slow this down, you can control it, but you need to be able to measure the eye properties very, very precisely to do that. That's one of the things that we're tackling as well. So this is Silide. There's a number of people here. Steve, that's our co-founder, he's sitting at the back there. Grant, Steve's brother, is also a co-founder, comes out of the optometry space. Trevor is another telecoms guy out of TRL and a few other startups. And there's me, that was the four of us who founded this about 8 years ago. Andy's our VP of engineering. Kylie runs sales and marketing. I think she's, as of today, commercial and clinical. That's new news to me. And there's Armin, who was our first employee. Back in 2013, he was a German backpacker, and we were looking for somebody who was cheap, but also had a PhD in optics. So we ran into Armin and hired him, and he was literally driving around Australia in a camper van with his girlfriend. And we persuaded him to come and join us and stay. And he's now married to his girlfriend, has 2 children, another one on the way, and has sold the camper van. So he's really sort of settled down nicely in Australia now. So we started the company 8 years ago and put the first patents in a couple of months after that. Took us a couple of years to get the technology demonstrated. It's called hyperparallel OCT. I'll explain what that means as we go through. We raised our first round of funding in 2016 and did the first formal product release at this research show in 2018. And we got a lot of interest there, and we actually sold a couple of machines to researchers around the world. Took us a year to work out how to make them before we could actually start shipping them. And on the basis of that, we raised some more money. So we basically raised a chunk of money from different sources. ISO 13485 is like, for the industry people here, ISO 9001 on steroids. If you've done ISO 9001, you're about a quarter of the way towards 13485. It's horrendous. We're Australian made. We've got the Australian little green kangaroo with the little green triangle with the gold kangaroo. That's actually really important for some of the markets that are in, particularly in Asia. See, Australian made and developed is seen as a quality product in Asia. So it's for us as a global company, it's actually a really good selling point. Last year, we won the Sir William Hudson Award of the Australian Engineers Australia. The William Hudson Award is the peak award that Engineers Australia give out each year for engineering projects in Australia. It covers things like liquid natural gas terminals up in the Northern Territory. It covers bridges. It covers everything. And our little machine, well, it's not little, it's quite big. It's about that sort of size. Won that for the complexity and just the things that we can do with it. And being in the medical space, all this certification, CE and TGA and FDA in the US is really important. You can't sell unless you get it certified as safe and effective. So OCT, we've talked about the fact that we're hyperparallel OCT. What is OCT? It's a way of imaging the eye. What you do is you shine light into the eye and look at the reflected signal back, and as a function of time or spectrum, you can pick up whereabouts in the eye you're looking through. It was invented back in 1991 by David Huang and came into first product in 96. Zeiss did that. To date, it's mainly been used for imaging the retina. That's the back of the eye. And so we started off by saying, okay, we'll do the harder thing, which is imaging the front of the eye. It's actually much harder. The retina's got a lot more reflectivity than the front of the eye because you want the photons to be hitting the back of the eye, so the front of your eye is very transparent. But that's where there's a lot of interest, because if you're doing cataract IOL lenses, if you're doing LASIK, you're doing any of those photorefractive vision improvements, you need to image the anterior segment. This is what a typical retinal image looks like. And this is sort of various layers within the eye. And this is the sort of thing without the false color that you get from an anterior segment OCT. So why do we do another OCT? This thing's been around for 20 odd years. Why are we doing another one? Basically, the existing OCTs had some limitations. There's an opportunity to overcome some of the problems. One of the problems is it takes a while for the OCT to do a measurement, and during which time your eye moves around about, it jitters all the time, your eye. And also as you get older, the people who have these cataract problems, they find it much harder to focus. Just look at me, on one thing at a time. The eye doesn't fixate as well. So it's very hard to do good measurements. You have a narrow field of view. The existing ones have a relatively small area of the eye they image. And because of these problems, you can't do the quantitative measurements that you want. You actually want to measure all of the optical surfaces in the eye. Where are they? What's their radius of curvature? Are there any deformities or malfunctions on them? And that's why we say whole of eye imaging. We're imaging all of the optical surfaces in the eye from the front right through to the back. And if you can do that, then you can overcome some of the problems that that currently exist. And you can then start to use this OCT for helping you for refractive surgery. At the moment, there's 3 or 4 different measurements and different machines you have to do before you can start slicing and dicing an eye. If we can do that all in one, we can start to look at some disease screening and particularly start looking at myopia management. And there's a whole bunch of technologies around myopia management that we're really interested in. And this is David Huang, the guy that invented OCT. He really likes what we've done. Basically, this is the best new approach in OCT that he's seen for many years, solution for taking out all of the measurement errors. And so we're working with David in Oregon to try and prove out a bunch of these things in our clinical trials. So here is how an OCT works. So here's a traditional OCT. You take a spot and you scan it across the eye, and at each point you measure, and you measure effectively the reflection back off each of the interfaces that's there. And you scan that across again, and you do a raster scan across the eye, and you build up a picture. And obviously, if the eye moves at any point in that time, the raster becomes slightly misaligned, and you have to then track the eye and do a whole bunch of complicated and very imprecise realignment of all the scans. That's a traditional single spot. What we do is we actually take some technology that we knew about from the telecom space, which is micro lens arrays. That you saw that video of a micro lens array being aligned just now from Luke. That was a one-dimensional micro lens array. We use a two-dimensional micro lens array, and we do a bulk imaging of that. So we basically fill that micro lens array with a large beam and generate 1,000 spots. So we start off with one spot, generate 1,000. And then we're measuring all of these simultaneously by dispersing them across a 2D sensor or camera. So it's effectively a CMOS camera. We've got a spectrometer which disperses each of these spots across here. And we can measure from the intensity at each of these points effectively what the reflectivity is. That's a huge oversimplification. Steve, if you want to know the details, talk to Steve at the back. And from that, what we do is we take a snapshot, and we take 300 of these measurement sets every second. So we're acquiring 300,000 points a second of information about the eye. So this is 3 to 10 times faster than existing systems. And this is how it works. So we have the system here which automatically aligns the OCT with the patient. And then it projects this grid of lines here, which basically reflect from the various interfaces. And what we do is we dither it very slightly to fill in the gaps in between to give a complete image. And because these are volume images, we can align them very successfully. And then we can, from that, pick up these various surfaces and measure the distances between them, the radius of curvature, and so on. We'll talk about design. This is what our first instrument looked like. This is actually one of our engineers, and this is the initial design that we took out and put into our first clinical trial up in Queensland. And this is what it looks like now. Oops, back. This is what it looks like now, somewhat sleeker than this. And we actually won an award for this a couple of months ago, the Victorian Premier's Design Award for the quality of this industrial design. It's a beautiful looking instrument. This is an optics community, so I'm going to show very briefly and without any detail the complexity of the optics that's in here. And this is bloody complex. You saw those things that Luke had where he's got like one prism, a couple of pieces of optics sitting inside his box. This one has rather more optics sitting inside there. I'm not going to try and explain it because I don't understand it, but that's just to give you an idea of the complexity of the optical path that's inside there. So coming out of that, what we get is an image that looks something like this. This is the data that you get after taking the sensor data and doing a first pass processing on it. So you can see here vaguely the outline of the cornea, that's the front of the eye. And then you've got the iris here and the lens here. If you look at those in more detail, each of those is an individual scan across the eye effectively. So we're effectively getting this full volume image at once. So you've got the cornea, the iris and your lens there. And then you have to do a whole bunch of image processing to basically get all of these volume images aligned up and centered together. But because they're volumes, that's really easy to do. It says real easy because I'm not the software guys trying to do it. But it's much easier to align volumes than it is anything else when you're doing the alignment. Now I'm going to show a few examples. This is an example of cornea. There's a problem here. It's actually from one of our employees, actually our chairman. He's got a scar. He had a LASIK treatment. He had a scar. And what we've got here, this is the volume image we collect. And these are then, you're going to see slices that are taken through this image, which is just a computer generated slice through the image. So here we have the slice coming through and you can see this is the cornea, iris, here's the lens. And you'll see up there, there's that corneal scar coming from a problem with his LASIK. And now we're going from right to left here. And then this one is going en face, so it's going in the Z direction. So you can see the cornea shape here. And here's the iris and there's the lens in there. So we're looking at slices through this on the way down. I'll skip through this one. This one is looking right into the corner of the eye. So this is very high resolution, looking into the corner of your eye where the cornea sort of meets the iris. Looking into this angle just here. If you can see that angle, you can look out for problems of a thing called closed angle glaucoma, which is a problem with the eye pressure increasing. And there's another serious cause of blindness. So we can actually see right into there very, very precisely. And we can also look at the retina. So here we're now looking at our retina. And this is the retina, that's the fovea, that's the most sensitive part of the retina right in the center. And we can see there, that was the foveal pit. You'll see as we go the other way, here comes the foveal pit just here. That's where you're most sensitive. It's a bit like what Baraja does. You have this region in your eye which is much more sensitive. That's where all your rods and cones are concentrated. And then this is finally another person. This is a problem that they have. You'll see up here, this is somebody who has toxoplasmosis, which is a disease you catch from cats. And in this case, they've been incredibly unlucky that the plasmosis is actually right on their fovea, right on the region of maximum sensitivity and maximum resolution of the eye. So they can't actually focus on anything with this eye, but we can still get some tremendous pictures of this, as you'll see as we scan through. That's the damaged region, the fovea. You'll see it again in this direction. Here's the damaged region going to come up around here. That's the damage that you can see and going down in the Z, coming up in the Z direction. It's just like a pit in the back of the eye. That's impossible to image using any other things out here. And this is a final thing. This is looking at blood vessels in the eye. The eye is an amazing window into your overall health. You can see blood vessels very, very clearly. You can use this for looking at any coronary issues. I have a friend whose leukemia was first diagnosed by looking at blood flow in his eye. You can see all these things because you've got transparency through into the eye. And you've also got transparency into the brain because the optic nerve is an extension of the brain. So you've got the ability to actually look at what's happening to brain tissue in the eye if you can do the measurements precisely enough. And that's the trick that we're working towards here. So here, this is looking at the cornea. So this is your iris, and this is the lens in the center. And what we're looking at now is the blood vessels in here. And you can see again, as we run the scan through here, this is artificially colored. You can see the actual blood vessels in the iris around the edge of the cornea here. And now I'm scanning the other way. And again, you can see there's not a lot of blood vessels in there. It's a very hard measurement to do. It looks quite easy in this one, but it actually is a really hard measurement to try and do. And this is the first sort of real good angiography of the cornea that's been done on a commercial type of machine. And the very last one is this one here, where we're looking at the whole eye. So this, you've taken the eye and you've pulled all the top and bottom eyelids open so you can see the whole eye at once. And this is done by stitching together multiple volumes at taken at different angles. And you have this magnificent view of the eye all the way out to the edges in both directions, which allows you to do some really interesting things. There's a company, for example, called Mojo that are trying to develop a contact lens, which allows you to do, basically, it's like Google Glass, but a wearable contact lens. This is the sort of thing that a company like that would be very interested in, because you can see exactly what's happening to the eye over a very large area. Okay, so that's a very quick overview of Sight. Happy to take any questions about any of that. I've got a little bit.
I don't think we have time for questions, unfortunately. It was
Pick
very,
up your pizza.
very interesting. Pizza is outside, so while Simon and Steve go, you can probably try to corner them and ask them your questions while you do that.